It's my pleasure to introduce Paolo Faglia, who will be talking to us about non-separability, local causality, and the criterion of reality.
Thank you. So first of all, I want to thank Lev and all the organizers because it's been an absolutely super interesting conference, and also the food, I want to note, has been actually amazing. So thank you very much. Anyway. So in this conference as well, but we hear a lot that Everettian quantum mechanics is local, and that's one of the perks of EQM. We love it. So the question that I was interested in is Everettian quantum mechanics the only realistic local interpretation of quantum theory? And a couple of years ago, I stumbled upon a paper by Kai and Kelvin McQueen that, roughly speaking, attempted to prove this statement. And so, really interesting paper, and I wanted to explore it. Unfortunately, my aim here is to try and disprove the theorem that they attempt to prove. And in doing so, I will once again clarify the very troubled relationship between local causality and separability. And I will offer as and at the very end, I will not disprove, while I will disprove the theorem in the sense that I will attempt to show that it doesn't go through, I will not disprove the claim that quantum mechanics is the only Everettian quantum, Everettian quantum mechanics is the only local realistic theory. But I will very quickly, I won't have time because it's a very short talk, but I will just cast doubts on it. And so the outline of the talk, I'll start by quickly presenting the Waegell and McQueen theorem, and I will try and show it that the theorem is wrong. I will use decoherence-based Everettian quantum mechanics, so sort of the quantum mechanics that Simon and David Wallace and all the people at Oxford take as the Everettian quantum mechanics. And I will try to show that it exposes a fallacy in one of the inferences of that Kai and Kelvin McQueen make. And then to cast out just briefly on the question of whether Everettian quantum mechanics is the only local realistic interpretation, I will just mention that maybe we should try and look at relativistic dynamical collapse theories, because that might be a new case. So let's get started. The Waegell and McQueen theorem. So what they're trying to do is they start with the GH-Z correlation. So Greenberger, Horn, and Zillinger in 1989 realized that you can get sort of similar correlations, similar non-local correlations to the one that Bell and EPR people talk about by entangling multiple particles, multiple systems. And what Waegell and McQueen want to say is that any theory that can correctly predict the GH-Z correlations has to give up one of the following three principles: local causality, no superdeterminism, and one world. Now, local causality is, as they define it, as Kai and Kelvin define it, is the statement that there can be no cause and effect between space-like separated events. So essentially, the denial of superluminal causation. No superdeterminism, I won't be particularly interested about in, so it's just roughly the statement that there can be no retro-causality and no fine-tuning. And the one world statement is that, roughly speaking, there's a unique outcome. So I call this statement, I mean, actually, Kai and Kelvin McQueen call it the which way statement. And so that's what they're trying to do to prove it. And they prove it by assuming local causality, assuming no superdeterminism, and the GH-Z correlations, and proving a violation of one world. And this is essentially logically equivalent to the which way statement. Now, the first step of their theorem is to introduce a background assumption, the criterion of reality, which is essentially the same that is introduced by Einstein and the EPR in the EPR paper. So if a system response to interventions can be predicted with certainty, then there is an element of reality which determines that response. Just very briefly, I wanted to note that it is a non-trivial assumption that a lot of people, I think, would reject. I think Cubism and Healy's pragmatism would reject the criterion of reality, and possibly maybe Michael Cufaro's informational view. But so maybe it would be better to reformulate which way in a sort of which way starred claim, according to which any theory that can correctly predict the GH-Z correlations violates one of local causality, no superdeterminism, one world, or the criterion of reality. And essentially, it seems to me that this is a quite nice statement, that encapsulate in a sense, the statement that Everettian quantum mechanics is the only realistic in the sense that it satisfies the criterion of reality, local in the sense that it satisfies local causality and no superdeterminism theory that there is. Now, briefly noting, local causality as defined by Kay and Calvin McQueen is not the local causality as defined by Bell. So when I mention local causality, just keep in mind local causality equals no superluminal causation. Okay, well, the second step of the theorem is the one that I will be focusing on, and it's, I think, the step that fails. So they argue that the criterion of reality and the conjunction of the criterion of reality and local causality implies the localized criterion of reality, which is as follows. If an intervention and response happen in a finite region of space-time, and the response can be predicted with certainty, then there is an element of reality located only in that region that determines that response. It's clear the role that the criterion of reality is playing here. Perfect predictability, the response can be predicted with certainty, then there is an element of reality that determines the response. That's fine. And the only thing that changes is that the intervention and response happen in a finite region of space-time. And so it looks like, if I'm correct, but I might be wrong, it seems like the reasoning is, well, it happens in this space-time region, so if the element of reality that determines the response in such space-time region were to be located somewhere else, there would be worries for local causality. And so it looks like localized experiment, the conjunction of the fact that the experiment is localized and local causality bring about this localized element of reality. Just briefly, I think it's worth maybe giving a philosophical flair characterization to the elements of reality. And it seems to me that an element of reality can be characterized as an agent-independent physical property of a system. And if it's localized, it seems to me that it can be characterized as an intrinsic property of a system which is wholly located in a given space-time region, in the one that we're interested in. I will now go a bit quickly because unfortunately I don't have much time, and I have no quibbles with the rest of the theorem. The third step is that they prove that systems in the GH-Z state individually possess spin X and spin Y localized elements of reality, and it's quite easy to see why, because there's correlations, so given that there's perfect correlations, you can predict with certainty, and given that the experiments are localized, there's a localized element of reality. And finally, they sort of consider, some counterfactual scenarios, some measurement scenarios, and they say, well, let's take three systems in a GH-Z state that's given to Alice, Bob, and Charlie, and put them as space-time separated locations, and then they perform experiments. And then, say they perform an experiment in the X direction, and there's going to be a constraint imposed by the GH-Z correlations. But suppose instead they do a measurement in the YYX, and they look at some different measurement scenarios, and then it turns out that the element of reality that was derived in the first scenario is different from the element of reality that is derived in the last scenario. And so, but this element of reality is supposed to determine the same outcome. And so it appears that there's no unique outcome, in fact, and that one world is violated. It looks like, they assume local causality, no superdeterminism, GH-Z correlations, the criterion of reality, and they derive a violation of one world. And this is equivalent to proving the which way star claim. Now, what I want to say is that I think step 2 is mistaken, because the conjunction of local causality and the criterion of reality does not imply the localized criterion of reality. And so the Waegell and McQueen theorem does not prove which way, which doesn't mean that which way star is false. I'm just saying that the theorem doesn't prove it. I will present a counterexample to step 2. So I'll illustrate why step 2 is wrong by presenting a counterexample. And the counterexample that I used is a decoherent, what I call the decoherence-based Everettian quantum mechanics, so DQM, which is the one that we've been talking about with David Wallace and Simon Saunders, and I'll characterize it more in the next slide. I will show that DQM satisfies local causality, that DQM satisfies the localized criterion of reality, the criterion of reality, but it does not satisfy the localized criterion of reality, and so it falsifies the second inference. Now, I won't go into too much detail about DQM because we've been talking about it for a week, and we all know what it is, but I will use two features of the interpretation. I will use first the feature that the density operator of a system, whether pure or impure, so whether reduced or pure, is a complete representation of its intrinsic quantum mechanical properties. This obviously leads to a non-separable ontology, in which the intrinsic properties of a joint system do not supervene on the intrinsic properties of the individual system, of the parts. I just want to briefly note that the fact that the object is non-separable, it does not mean in any way that I cannot talk about the parts as objects, and I will talk about the parts as objects, and I will talk about the intrinsic properties of the parts. So sometimes there's, in the literature there has been, I think particularly in the past, there's been talk of, well, the quantum system is non-separable, so there's not really two quantum systems, there's only one. And maybe that to an extent is true, but there are two systems that have intrinsic properties, and these intrinsic properties, I take them to be completely described by the density operator, by the reduced density operators. And once again, the reduced density operators will not give us the state of the joint system because of non-separability and because of entanglement correlations. And the second element that I think is crucial to the analysis here is that branching occurs through decoherence. So I quote David Wallace here. When some microscopic superposition is magnified up to macroscopic scales, it leads to a branching event which propagates outwards at the speed of whatever dynamical interaction is causing decoherence. So what is crucial here is that it is the process of decoherence which makes definite the outcome of a measurement with respect to a system. And branching is therefore localized and dynamically defined. Now, I'll briefly argue that DQM is local in the sense that it satisfies local causality. And there's a very easy principle argument that shows that there's no mechanism, which, and it's something that I think Don Page was mentioning before, basically. We've got a unitary dynamics, we've got local Hamiltonians in the sense that they are point-like interactions, and the no signaling theorem tells us that the density operator of a system, of two separated systems, won't be affected by applying local unitary dynamics to one of the two. And given that the density operator represents all intrinsic properties, we've got that there's local causality. What you do to a system will not affect the intrinsic properties of a separated system. But Faglia, who's not here right now, was telling us in the first day about principal explanations versus constructive explanations. There's a sense in which maybe this is a bit unsatisfactory because I'm just giving the principles of why DQM satisfies local causality. But how is it possible? How is it possible that entanglement correlations, which seems to be non-local, how can they arise without local causation? And well, firstly, we're all Everettians, and so we all know that all outcomes occur, and as Timpson and Brown put it, there's no dash to ensure agreement because they both occur at both space-time locations, so there's no need to enforce the correlations at a distance. Given that the outcomes are ontologically determined with respect to a given system or a space-time region, by decoherence branching out the system or branching out the space-time region, they will be ontologically undetermined in the two space-time locations, until decoherence makes them determined. So I borrow here a plot from David Wallace's book, and we've got the measurement Alice and Bob measuring, and the two sort of decoherence wavefront represented on the plot. Now, if you consider Alice on the left, when she measured the outcome of Bob's experiments will not be determined at the space-time point at which she measures. It will only be determined in the overlap of the future light cones. And so there's no need to, once again, there's no need to enforce the correlations at a distance, at a space-like distance. They will only occur in the future light cone, and they will occur through the appropriate joining of or splitting of branches. So, the branch in which Alice obtains up will match the branch which Bob obtains up. And how do we ensure that the right branches join or split? That is thanks to the non-separable entanglement properties, which locally cause the appropriate joining or splitting. So the entanglement properties that sort of are a property of the joint system of Alice and Bob will then locally determine in the overlap of the future light cones how the branches join and how the branches split. And you can see this in a toy experiment when you think of the two Alice and Bob systems when they reconvene together in the future light cone. They will perform an experiment to verify the directions of the other experiment, which spin did they obtain on the other hand. And locally, at that point, the joint system has intrinsic properties, the non-separable entanglement properties, which were non-local at the origins of the experiments. And those will locally cause the appropriate joining or splitting of branches. So I'll take it that we can take DQM as locally causal. I'll just look at now instead of the criteria of reality. So we've got the criterion of reality. If a system response to an intervention can be predicted with certainty, then there is an element of reality which determines that response. And I want to see if this is satisfied by Everettian quantum mechanics, decoherence-based Everettian quantum mechanics. And we need to make some clarifications first, because it seems to me that it's slightly ambiguous in the context of Everettian quantum mechanics. So first, who predicts? Clearly, on which branch is the prediction being made? And there's no specification, and it seems clear that anybody is implied, that anybody who predicts with certainty. So let's call this anybody yes. And there's also a question, prediction with respect to whom? With respect to which branch? And it seems clear that the criterion of reality is thought of as if Alice, after obtaining spin up, is thinking about what will Alice obtain with respect to me? So it's clear that the prediction is with respect to the person that is making the prediction. So the outcome with respect to the person that is making the prediction, sorry. So we come up with we deambiguate our criterion, and we obtain if a system responds to an intervention with respect to S can be predicted with certainty by S, then there is an element of reality which determines that response with respect to S. And clearly, the criterion of reality holds in DQM because the dynamics is entirely deterministic. So the fact that Alice obtains spin up and can predict, when Alice obtains spin up and she predicts that Bob obtains, say, spin up, that is determined by the joint state of Alice and Bob and the unitary dynamics. That is perfectly determined. And so the criterion of reality holds. Now let's take a look at the localized criterion of reality. And we have that, if we disambiguate it in the same sense, we have the following criterion. If an intervention and response happen in a finite region of spacetime, and the outcome of the response with respect to S can be predicted with certainty by S, then there is an element of reality in the region that determines the outcome of the response with respect to S. This is not satisfied by decoherence-based Everettian quantum mechanics because the localized elements of reality at Alice's and Bob's location are the reduced density operators, or are represented by the reduced density operators. And these reduced density operators will not tell us the entanglement correlations. And so there is, when Alice predicts with certainty that Bob's obtains up, at Bob's location, there is no element of reality which determines that with respect to Alice, the outcome of Bob's experiment will be up. Because what determines that is the entanglement correlations. And those are properties of the joint system, not properties of the individual systems. Thank you. So I'll wrap it up. So step 2 is, I think, does not follow because it doesn't seem to me that local causality and the criterion of reality imply the localized criterion of reality. And once again, this is because of non-separability, because there's non-separable properties which allow for a local explanation of the entanglement correlation without having to have localized elements of reality at each space-time location. Now, it seems to me that the paper by Kai and Calvin McQueen does not prove which way start. And however, obviously, I've provided as a counterexample an Everettian theory. So I have not disproven which way start. And it may be the case that which way start is true. And I think here it is apt to think of a footnote that Brown and Timpson put in one of their papers, Bell on Bell theorem. And they say, we'll leave it as an open question whether or not in any non-separable theory which is dynamically local and predicts Bell correlations, uniqueness of measurement outcomes fails. And it seems appropriate that the remaining step to prove, if we want to prove which way star, is to prove that, as Timpson and Brown wonder, is to prove that non-separable interpretations which are realistic and dynamically local or satisfy local causality, that they are all Everettian. However, I have just a hint of doubt, and I think recently in the past month and a half, I've been looking at foliation relative dynamical collapse in frameworks, which have been defended and developed mostly by Myhrvold, by Wayne Myhrvold. And it seems to me, at least the claims that Myhrvold makes, is that there are realistic interpretations of quantum mechanics. They are non-separable, non-Everettian, and locally causal. On this doubtful note, I wanted to end my talk.
Paolo, I thought that was a very nice exposition of everything. So first I want to say that Kelvin and I agree with you about some of the weaknesses of this. We already have our new version of this paper. We've tried to take away the word predict. That shouldn't be relevant to who is predicting what. But the fundamental thing is that I still disagree that the reduced density matrices exhaust all of the intrinsic properties of a system. I've been over why I disagree with that in my own talk, so I don't want to repeat my talk again, but I think that really is the bone of contention. And there are some people in this room who seem to have both views. Do you think that it is reasonable to argue in any way that having a non-separable reduced density matrix? So I agree that if you have like two particles that are separated, they do have local identities, they have separate properties, but if there are spin states that are entangled, do you think that the reduced density matrices of their spins are in fact exhausting their local properties? And do you think there's any room for argument about that?
I'll say thank you. I forgot to say I would, that I should have said that you and Calvin McQueen have a new paper in which you make similar points. But it seems to me that regardless of what well, it seems to me plausible that there can be a non-separable ontology, and it seems to me plausible then that the intrinsic properties of a system may not supervene, and including the localized, the spins may have entanglement correlations which do not supervene, just as the relation of being 10 meters away from you does not supervene on the properties of you, on the intrinsic properties of you and the intrinsic properties that I have. whether I believe that's the best, I'm just making a sort of a more formal claim here that there's no implausibility argument, it seems to me, against the non-separable interpretations. So it seems to stop the inference from going through.
You use so many definitions, so I'm a lost little. First, maybe just quickly, as you are, I think, 1 week you are here, is my many words is different from what your decoherent many words? Because I thought I came to agreement that there is no really difference. I just my decoherence to internal degrees of freedom, and then we are equivalent. Or not?
I didn't want to include you there because I haven't read enough of your papers, and it seems to me that you guys ended up being in agreement, but I didn't want to step on dangerous territory. But it seems to me that you guys are in agreement, yeah.
Just no. But my question is probably the example which you showed from David's book. If I understand, you have APR, and then Alice measures and finds it's up. Then, you know, you're not read my papers, but now I can repeat. In the moment Alice found up, in her world, there is a reality immediately, space-like separate, that Bob is down. Definite, no, you don't have to wait until they meet. In Bob, because she can bet, like on experiment performed in the space-like separate space about Bob's spin, and she will put money on down. She will put $1 million.
Yes.
She knows it's down.
Yes.
They don't have to wait. And it looks like you're trying to say, no, it's not. So your words, it's kind of the words which we had in the last talk. You are in this framework when your words are space only, they are not all over, because Everett word, many word is all over. The whole story. You're right, psi of the universe, superposition of alpha I, psi I. Psi I is description of the whole space. And this is, every psi I correspond to a word. And in this word, Bob has down. Well, this other thing, I don't know what it is. It's kind of, it's not, it's a new description, which is not many words. I don't think it's attractive in any way whatsoever. You try to describe universe, but some kind of this area, other area. No, the word is everything. The word is supposed to be a layman word, and when layman says that the word is everywhere.
Well, see, I don't think that the world disappears when I don't think that the world disappears once the experiments are performed. But I do think that when Alice, I mean, this is my reading of David Wallace's list views, and I hope that I'm not completely misrepresenting him, but he's not here. Yeah, right. But it seems to me that according to his idea, or well, let's say my idea, right? According to my idea, there's when Alice performs a measurement, until she is decohered by and until she's branched out by dynamical interactions, the
immediately decohered, of course.
By the dynamical interactions that started on Bob's side, she won't have, Bob's experiment won't be determined. So if you consider, like, you know, suppose that instead of doing up and down, they do some, you know, up, down, and then left and right, right? Suppose instead of measuring up.
No, we talk about simple case.
But that's a simple case. Okay.
So this is just really to follow up on what Lev is saying, and to go back to your slide from David's book with wavefronts, is that those wavefronts are a verbal construction in David's theory, but they're not in the math anywhere. I said that in my talk as well, but it's like a contrivance that they've added, you know, based on ideas that the correct successor theory should be the Lorentz covariant quantum theory, but they don't have a Lorentz covariant quantum theory. They have never specified one. That's all I want to say.
Okay, so well, maybe this is in conflict with what Kai's just said. And I think to just try and clarify the interchange between Paolo and Lev. I mean, just to start off, Paolo, I think you'd say that when Alice does her measurement, Bob is in her world, yeah? And Bob's measurement is in an indefinite state, right? Yeah. What? Well, if Bob does the yeah, well, we'll talk about the particle. If Bob does the measurement, he's in a macroscopic superposition. Well, but then that is blatantly in conflict with your definition of world, because you say in a world is defined by everything being in macroscopically definite state. And from Paolo's point of view, you've got the macroscopic indefinite states in her absolute elsewhere. And in general, you know, there will be, you know, the more distant you go into her absolute elsewhere because of quantum events, there'll be loads of macroscopic superposition. And so that's absolutely in conflict with your view. In conflict because you're defining a world as being macroscopically definite everywhere out to infinity.
I think I agree with what Paul just said, but yeah, I don't have any further comment.
I mean, just to say, I mean, Lev, you seem to agree that it was okay to have decoherence with respect to internal degrees of freedom of a system, but you argued vigorously against that last night when you and I were talking. So I just don't know what you think anymore. Well, we had the photomultiplier, remember, in a box. I'm the only one drinking it. So we had the photomultiplier in a box, and you refused to permit me to integrate out the radiation, the thermal radiation in the box. So anyway, I don't want to revisit it. Lev will never finish. But just, can I just say something about the business of the wavefront propagating out? I agree that there's no such wavefront. But if you think what decoherence involves, so if you think about it in scattering terms, which is normally the way I like to think. So decoherence, it comes about through scattering of many, many particles in such a way that states of the local system can no longer interfere with one another because each of them is tensor product with a big state of the scattering particles, which is orthogonal to the other one and so forth. So that scattering and thereby the particles propagate out and they in turn scatter, they in turn give rise to whatever photons that is. That process, we have very good reason to believe, could not be superluminal. I don't have a wavefront in the maths. I'm just looking at how correlations propagate. And okay, so sorry, Paolo, I'd like to talk.
Thanks. Yes, I was curious about Rovelli's relational interpretation. If that, according to him, it's a local interpretation. It's not really. I mean, it's local in space. It's not really clear. It's local in time. So, yeah.
But see, I personally, I've been reading and thinking about Rovelli's relational quantum mechanics for a while. I can't say to have managed to string together a really, you know, sort of definite set of claims that are made. But it seems to me that if one takes it to be realistic, so like a sort of interpretation where there's a more realistic stand or scientific realism, I don't think the locality claim would go through, because the fact that the entanglement events are relational doesn't make them disappear in space-time, you know. And so I'm a bit dubious about that. If one takes a more pragmatic sort of stance, which it seems to me the one that Rovelli is taking on more lately, of taking the quantum state to not represent anything, to be sort of like a mathematically useful device and these sort of things, it seems to me that probably it would be local, but so I think it would be local. It would not be a realistic theory, so it'd come out of this question that I have, and I was trying to explore, is every local realistic theory Everettian? But I have a little bit of confusion about if the wave function represents nothing, then how do we understand when the when the entanglement event occurs and all that sort of things? I find it a bit confusing.
Right. Thank you.